All right. Hello, everyone. Good evening, good afternoon, good morning for me, I guess. Thank you for coming to CodeGen 21 virtual virtual edition. My name is Jimmy Bogard. You can find me on Twitter at @jbogard. You can find this presentation and a lot of other stuff I do at github.com/jbogard. And I blog about this topic and a lot of other ones at my blog at jimmybogard.com. I'm an independent consultant out of Austin, Texas. So you may hear some Texas accents here and there, y'alls and such. I'm also chief architect at an independent consulting firm here in town called Headspring. And I do a lot of open source and other stuff related to this topic. So yeah, today we're going to be talking about refactoring towards distributed systems resilience. So this talk, like a lot of my other talks, is really about something that happened in my day-to-day work. And it was interesting enough, I thought I could share the story with everyone else. And so this one in particular starts out with my coworker, Bill. We'll call him Bill because, well, that's his name, actually. I don't have to change it. And he came to me one day to my desk with this like really worried look on his face. Like he was almost sweating. He was so worried. Now, Bill is just a really kind of even keel sort of person. He doesn't show a lot of emotion. Like he didn't even tell us that his kid was born until like a month later. Like he just keeps everything inside. So when he came up to my desk and had this super worried look on his face, I knew something was really wrong. And he said, Jimmy, I'm at this application that we're supposed to go live in a couple weeks, and I'm reviewing the code for a customer who just wanted to get a quick code review before they go to production, make sure everything looks okay. And he said he saw something in the code that really worried him, and really worried him, like, you know, when he's sweating, his worried look at his face, and knew like, okay, this is something wrong. I said, okay, Bill, let's go grab a conference room. Well, this is back when we had conference rooms and we had offices and such. And we said, let's go get a conference room. Let's go take a look at the code together and see what got you so worried. And he showed me these 6 little lines of code. And these 6 little lines of code didn't seem that problematic at first glance. But when we started digging in, we saw that these 6 little lines of code hid a very enormous problem that was going to be for this customer. So let's take a look at these 6 little lines of code. Okay, so I have dumbed it down a little bit, but effectively it was these 6 lines of code and the most important function in the entire application for this customer. And so in this application, it was a reservation site. And the most important part of this site was when you click the button at the very end of making a reservation, when you put in your credit card information and your personal information and you click pay, and when you click play, that's what these are the 6 lines of codes that get executed. So this is an MVC application. That's not as important. What's important though is that these 6 lines of code are the ones executed when you click the button to say pay the money and do the stuff. So let's look at these lines of code one by one. So first one is just, I have a shopping cart, I click pay. So the first thing I have to do is load up your customer information from the database. Nothing too interesting there. The next one is to create an order from a cart and your customer details. So it takes your cart information, your customer details, puts those together and creates an order in the database. Now this is where things get interesting. So after we create the order, we need to actually charge your card. And for us, we were using a third-party payment gateway known as Stripe. It's very popular, very robust, very resilient. And so it has a very lovely, easy to use API to be able to make and process payments. So that's the next thing we do is post a payment to Stripe calling their API. Now, once we post your payment, the next thing we need to do is send you an email to tell you, hey, we got your payment, your order is good, everything looks great, here's your order details. For that, we're using another third-party service called SendGrid. We chose SendGrid because that is a very great API. It has a great reputation for having a great uptime, and it sends emails very quickly. So that's the next thing we do is send a thank you email via SendGrid. Now, in this application, we don't actually process your order ourselves. We're going to use some downstream systems to actually process that order. And we don't want to communicate with those systems directly because they're kind of old and crufty and like COBOL mainframes and junk. So we're not going to talk to those systems directly. Instead, we're going to use a message broker to do so. So for that, we're using RabbitMQ to send a message via RabbitMQ to these downstream systems. Finally, at the end, once we've done all these things, we need to actually do something with the customer, say thank you for your order. And so that's the last thing we do is we redirect the customer to a thank you page. Now, outside of all of this that you don't see in this specific code, is every time you make a post to our application, we actually just automatically wrap the entire operation in a transaction. And this is just to help developers. If they forget to do the transaction themselves, then we just say every time you post information to the website, we're going to just go ahead and wrap everything in a transaction. So somewhere in an action filter or something, there's something that calls into Entity Framework that was ORM to say, go ahead and save the changes. Now, looking at this, looks pretty straightforward, right? It's like 6 lines of code, calling a few services, whatever, saving a transaction, no big deal. There's a problem here. This code assumes that every single line that we've written here is going to be successful. And there's one thing that I know dealing with distributed systems, and actually systems in general, is that failure is a reality, and failure is always an option in these systems. And if we just simply ignore failures or pretend that they don't exist, then bad things are going to happen. And this is why my coworker, Bill, was so worried, because there was nothing in this code that dealt with any kind of failures whatsoever. I mean, we're using ASP.NET Core here, so there's some kind of exception handling. So if something goes wrong, the user might see like an error page, but that doesn't mean the systems behind the scenes have any kind of ability to deal with these failures. And so our code is not even attempting to deal with those failures. So I said, okay, Bill, let's just map this out in the whiteboard. So let's just write down all the calls to all these different systems. And then one by one, let's see how the system responds or behaves to one of these calls failing, and see if that's going to be a problem or not. So we mapped it out. We said, okay, we got 5 calls effectively. We've got a call to the database to go get your customer details and save your order. So just say that's effectively one call. We have call to third-party providers and third-party systems. We have call to Stripe, call to SendGrid, and call to RabbitMQ. And then finally, around the entire database activity is a transaction. So let's see, call by call, what happens when each of these calls fails. Now, I'm very deliberate about my use of the language here, where I say when and not if. If I say if a call fails, then everyone gets their happy ears on and thinks that, well, those calls can't fail because databases don't go down, right? Stripe doesn't go down. If Stripe goes down, well, then the whole world goes down because everyone has their payments through Stripe. That's not true. Like, things absolutely do go down. Like, Google goes down. And if Google can go down, then absolutely these other systems can go down. And of course, our own systems can go down because we don't have the money to put into resiliency as Google does. So we need to actually go call by call and see what happens when, not if, when each of these calls fails. So how about the first one? What happens when this first call fails to load up the customer details and create an order in the database? Well, it's not good, right? We hope that our own database stays up, but when that call fails to the database, well, we've got everything wrapped in a transaction. So the transaction rolls back, an error is shown to the end user, which is not a good thing. Like, the customer's probably pretty worried that they just put their credit card details and then they hit save and something went wrong. But at least the entire system is consistent. That is, from each of the systems perspective that we're looking at here, all of them agree that an order has not been processed. How about the next one? What happens when Stripe fails? So we've retrieved data from the database. We've inserted a row into the database. We made the first call out to Stripe and that call failed. Well, no money posts to Stripe because that call failed. However, we do have our database wrapped in a transaction. So when we get an exception, that transaction rolls back. And so the overall system is still consistent. Now, that's not entirely true because Stripe is an API using HTTP. And so it could have been the case that we made a call to Stripe and the call actually succeeded, but we just didn't wait long enough for a response. We'll skip over that. We'll come back to that a little bit later. So let's just assume that we make a call to Stripe. Stripe is just down and we get some kind of service unavailable response from that call. Okay, now this is where things get interesting. What happens when SendGrid goes down? So this is why Bill had that really worried look in his face. So we have made the call to the database. We tried to insert a row. We made a call to Stripe, but Stripe succeeded this time. So we've actually charged the customer. We tried to tell the customer that we've received their order, but they call us SendGrid failed. So we get an exception. The transaction rolls back. However, the customer is still charged. So the customer sees that error page, like something's wrong, like, uh-oh, something's wrong, I should contact customer service. So what do? They call customer service and say, I got an error submitting my order. That's great, what's your order ID? I don't have one because it never inserted the order into the database. Okay, let me go ahead and look it up. Well, I don't see any order in the database either. So there's nothing for your customer, it says no orders for you. So I think everything is okay. 5 days go past, the customer looks at their bank account and notices, wait a second, I got charged for that order. So they call customer service again. Hey, you said nothing was wrong, everything was okay, but I got charged. Oh, okay, what's your order ID? We don't have one because it never actually entered the order into the database. So customer's upset. They go onto Yelp or Google reviews, leave a horrible review for our business, and our customer service goes down. Our business is upset. And they say, why, oh, why can't you build a better system? Okay, let's keep going. What happens when RabbitMQs goes down? Which is perfectly possible to happen. Like the disk could fill up. We could have some DNS problems connecting to RabbitMQ. Doesn't matter why, but let's just suppose that RabbitMQ goes down. This is where things are starting to get worse and worse because we've tried to insert a row into a database, but that's wrapped into a transaction. We call out to Stripe, we charge the customer, we call SendGrid, SendGrid succeeds. We actually email the customer, thank you for your order, and here's a link to see your order details. But we try to notify downstream systems that we want to go ahead and process the order. That call fails, which means we get an exception, the transaction rolls back, and now the system is very inconsistent. So the customer now, they see an email that says, okay, thank you for your order. Here's your order details. They go to click that link, but that link doesn't work because the order doesn't exist. The order never actually made it into the database. So they've been charged, they've been emailed, but nobody knows about the order except for their bank account that shows, oops, we've taken your money. So again, bad customer service, bad reviews, bad for business. And finally, the worst thing that can happen. What happens when the database fails? Now this is assuming that the first call succeeds, but the next call when we go to actually commit the transaction, that fails, which is perfectly possible to happen because we could have things like a connection succeeding to an insert, but then a connection failing when we actually want to commit the transaction. The transaction can fail as well. Let's say we've had, I don't know, database constraints or something like that, that when we go to commit the transaction, something trips there and then fails for us. So we have charged the customer, we've notified the customer, and we've told downstream systems to go ahead and process this order. But the transaction rolls back, the order's never actually inserted into the database, so the system is just now royally screwed at this point. We don't have any record of your order. Downstream systems go to process the order, they go to get the order details, no order exists, and now everyone is very, very upset. So what do we do here? How do we fix this? This is why Bill was sweating so much. I go, well, how do we fix it? We're 2 weeks from production. How do we fix this problem? Well, today, as it is, the code was just shrugging its shoulders. Meh. But just like throwing up your hands, shrugging your shoulders, saying, it's probably not going to fail. You know, these are rock solid systems. They don't go down. But just kind of, throwing up your hands and giving up is probably not good for business. Because when things go wrong here, as we've seen, walking through each of these calls, none of them result in a good customer experience, and all of them really result in the customer being mad at the business and complaining to someone, and our reputation is suffering. So, going back to here, the real problem here is that we really want all of these calls to either succeed or fail together. And the way that most people would do that is just say, well, let's just do a transaction, right? Like let's just wrap this whole thing in a transaction. So all of it succeeds or all of it fails. So that little line down here, let's just stretch it over. There we go, problem fixed. Now we have Stripe, the database, SendGrid, RabbitMQ, all wrapped in a transaction, and everybody's happy, right? Well, no, because we can't do this. We can't put Stripe in a transaction. We can't put Singer in a transaction. And we certainly can't coordinate transactions between all of these different things. Really, really smart people have tried to do this. They've tried to wrap multiple resources in a single transaction. There's academic papers and PhDs dedicated to the subject. But the problem is all of those kinds of efforts ultimately fail in a world where things are a bit messier and have these different third-party services that have nothing to do with each other. So you could try to put some kind of protocol or communication service on top of these things to try to put things in a transaction. But the problem is that those protocols are still not bulletproof 100%. And they all also require all of these systems to be very, very close to each other because they all require tight, very close, very fast communication. So we can't just do our PowerPoint architecting, dragging the box over and say, wrap it all in a transaction, because that's not how the world works. We can't just put the entire world in a transaction. And in fact, if we looked at the real world doesn't perform these complex multi-party transactions. They look like humans and people and civilizations. We don't do this because it's very complicated and it's very expensive. Expensive in terms of resources and expensive in terms of communication. The real world is a lot messier, and they deal with failures as they come up and with kind of very specific protocols and procedures when something goes wrong. So we need to go back to the drawing board, back to the whiteboard, and say, let's just assume that any one of these calls can fail and put together a strategy and techniques in place to deal with these failures when they come up. So let's plan for the worst. Let's just assume that any one of these calls will fail and put code in place to be able to deal with these failures as they come up. Now, luckily for me and Bill, we didn't have to invent all of these different ways for dealing with failures. And in fact, there's a very fantastic paper out there from Gregor Hope. He has a paper called Your Coffee Shop Doesn't Use Two-Phase Commit. A two-phase commit is the commit protocol for trying to put the world in a transaction. And what he said in this paper was, the real world doesn't use these complex transaction protocols between multiple parties. Instead, they have very specific strategies in dealing with these different failures. Now, originally, this was Starbucks doesn't use two-phase commit, which I know may offend some of the Italians out there. That's fine. But it also offended Starbucks because they didn't want their name dealing with like wonky distributed systems failures. So he changed it to Your Coffee Shop doesn't use two-phase commit, but the idea is the same. And so Gregor Hope, he had this observation that when he was sitting in a coffee shop, he noticed that what he was looking at was multiple parties involved in an overall transaction, which was you go into a coffee shop, you go buy coffee, and you get it sometime later. But it's not a single synchronous transaction that you observe when you're part of this business transaction. You don't stand at the counter waiting for your coffee. Instead, you kind of move to the side and your initial transaction of giving your order and paying your money completes. So he looked at this system, this overall business system, and said, well, what are the different ways that this system can deal with failures between this overall business transaction? And that's exactly what this paper covers. So he outlined 4 main options for dealing with failures between 2 or more systems. Now, the first option he laid out is simply to ignore the failure. So the idea here is that I have 2 actions that have to I have 1 action, to perform against 2 different resources. They're not transactionally bound. I perform 1 action against resource A. I perform the action against resource B. Resource B fails, and we simply ignore the failure for resource B. Now, you may look at that and say, well, why would we ever ignore failures for a resource? But there are cases where we don't want a failure of a distributed system to not affect the succeed or failure of the original resource. And we'll cover a few cases here in a little bit. The second option is a retry. That is, we perform an action against resource A, it succeeds, resource B fails, and instead of us ignoring that failure, we simply try that action again. Now, there could be cases where the resource B action is not retryable, and so we may have to have some additional logic to say, make sure that we can actually do this thing again, and it only results in the operation actually happening once. Option 3 is to undo. That is, we make an action against resource A, resource B action fails. And instead of retrying resource B, we perform an undo operation of resource A. Now the resource A action has already succeeded, so that transaction has committed. So we have to find some kind of logical undo operation for whatever that action was for resource A. So we may have to get a little creative here when looking at undo to understand what does it mean to undo an action. And finally, we can look at a coordinated transaction. So you can see here, this is basically a two-phase commit. We may not be using like an official two-phase commit protocol, but the general idea here is that we have some kind of third-party coordinator that first asks resource A and resource B to prepare their transaction. So they basically put their resources to the side, reserving them for the transaction to ensure that they can succeed. Resource A and B then tell the coordinator, yes, I'm good to go. I'm able to process this transaction. Once the coordinators receive the signals from A and B that they're good to go, then they send another signal to resource A and B to say, go ahead and commit. So that's where the two-phase commit, the term two-phase comes from two-phase commit. We have a prepare phase and a commit phase. Now, this looks complicated because it is, but we do have cases of this kind of transaction in real life. So when the stakes are high, when we really want to make sure that this kind of transaction can't succeed, then we'll often have a third-party coordinator in real life. So if you've had to like purchase property, an apartment or real estate, you will have a third-party coordinator, someone to broker the transaction between the buyer and the seller. And they're really there to ensure that the overall transaction completes. You can, of course, go straight from resource A to resource B, but typically you have some kind of third party that is there to kind of broker the transaction, ensure that the buyer and the seller agree on terms, and then once they both agree on terms, then they go ahead and broker the transaction. The coordinator does not work for free in real life, and the coordinator is not free in our virtual distributed systems world either, both in terms of resources and in terms of latency and in terms of communication. Lots more arrows, lots more communication back and forth. But it's still important to keep this as a possibility for dealing with failures. So our master plan for each external resource, examine the four possibilities, the four strategies, the four options, and pick the best option based on business requirements. Now, not necessarily just technical requirements, because each of the different options for dealing with failures is going to affect the user experience in some way. So it's very important that we also involve the business in each of our decisions. Now, I won't use terms like two-phase commit and distributed transactions, but we will talk about things in terms of the business, the business terms and how we're going to deal with failures and how the user is going to experience those failures. Stripe. So going back to our picture here, these are the 6 original lines of code, and line number 3 there, or 4, I guess, that's where we're making that API call out to Stripe. So option 1, ignore. So what would that look like? It would basically be a try catch around that Stripe call and just catch the exception, maybe log in, do nothing. Well, I don't know if the business would really be okay with us ignoring failed payments. Businesses run on money. That's like the most important line of code to run the business is to take the customer's money. So we probably don't want to just ignore a failed payment. I would throw it up there for the business, but it probably won't because they'll just give me this like really dirty look to say, of course we need to get money from the customer. Option 2, retry. So this is where you have to get creative with your Googling. Because retry, we need to make sure that the overall operation that we're doing, you call the API twice, we need to make sure that the overall result happens once. And there's a term for that, idempotent or idempotency. So you go to your Google, you Google Stripe idempotent and see what comes up. Well, luckily, there's a documentation page from Stripe about how to do idempotent requests. This is really critical here because we don't want to charge the customer twice. Charging the customer no times is better than charging the customer twice. Charging the customer twice, they're going to be twice as mad at us than charging us no times. So we need to make sure they only take their money once. And so Stripe actually supports idempotent requests. And there's a couple ways you can do idempotent requests, but the key thing is when I call them twice, they need to have some way to distinguish one call from the next. Now you could say, well, you know, if I just make 2 calls within a very quick amount of time, then they should just be able to figure out, well, those are 2 calls. Like just, of course, I'm not charging it twice. But we have integration scenarios where we may be charging a lot of people, a lot of different things, or even charging the same customer twice for 2 different operations. So we can't just look at the call and say, well, that's obviously 2 calls, or obviously 1 call that was just called twice. We need to have some way to distinguish between 1 call and the next. And there's a few different ways of doing that. One way is to have some kind of natural idempotency between the operations. So like turning on a light, I can say, turn on the light twice, and the light will only be turned on once, because once you perform that operation, the light is on. So if I tell you to turn on the light again, well, it's already on. So it's just a naturally idempotent operation. In this case, there's not a naturally idempotent operation. If I tell you charge the customer twice, they're going to get charged twice. So I need to have some way to identify individual calls. And to identify individual calls, I need some kind of correlation identifier for that call to say this call is the same as the next call, because there's something I'm identifying as distinct on this individual call. And so Stripe allows us. You'll actually give to it in a header an idempotency key. And this header just needs to be distinct for whatever logical payment operation that you're trying to perform. You actually see this in the real world. When I go to my coffee shop, they ask for my name. And that name is used to identify between one person's order and the next. And as long as there's not, 20 Mateos showing up at once, then I have a reasonable guarantee that I'm not going to get some other Mateo's order. Jimmy is a relatively unique name in the States, so it's pretty rare that I have 2 Jimmys coming in for an order, but they may ask for my last name as well if they see a bunch of Jimmys coming in all at once. So to avoid the kind of like natural idempotency problems, instead we can make something up, just create some idempotency key. And so if we go back and look at our code, we can look around and say, what distinguishes this logical business transaction from other ones? Well, for us, we actually have something. It's the cart ID. The cart ID represents the logical business transaction of processing an order. Each order is going to have a separate order ID or cart ID, and that is the thing that distinguishes between one order and the next. I should only charge the customer once per cart per order. So we can pass that in to our Stripe service and say, okay, this is my idempotency key. So if we call this method twice, the customer only gets charged once. Option 3, undo. Now, the last one was pretty easy to Google. I just say the name of the service and then idempotent, and then hopefully I get results. But for undo, there's not like a computer sciencey term for this, so I have to get creative. What does it mean to logically undo an operation of processing a payment? Well, there's a few different names for it. Chargebacks. Yeah, I think chargeback. But for payments, the big one is going to be refund. Refunds are paying the customer back for a payment that they've made. And refund, what I'll do is I just give the ID of the payment, and they will put the amount back on the card or post the payment back exactly the opposite of whatever they charged. So what they'll look like in my code is I'd have a try catch around like the main stuff of my operation. And if anything goes wrong, then I will call Stripe to say, go ahead and refund that payment. But that, in this set of code, that doesn't encompass everything that can go wrong, because if you remember way long ago, we said there's a transaction around all of this. So when we're dealing with distributed system failures, we need to really make sure that our code has all of the ways that something can go wrong. So I'm actually going to extend this to say, we're going to include the database transaction commit in part of our try catch, so that if something goes wrong with the database transaction commit cycle, then we'll go ahead and refund the payment and roll back the transaction. Option 4, coordinate. Now we said earlier that systems in general don't follow any kind of like distributed transaction protocols, which is true. Like you can't do like a 2-phase commit protocol, distributed transaction coordinated protocol with Stripe. But they may support something similar with the logical protocol of a 2-phase commit. And it turns out that Stripe does. They follow the authorized capture flow with a 2-step payment flow. And you actually see this in your bank statement. You may see at the top, you have authorized transactions and posted transactions or capture transactions. So the idea here is that you first authorize a charge. And what this is doing is kind of putting that money to the side, saying, we intend to take this money out. So it kind of puts it to the side. And then later on, it's confirmed, say, yes, now I want to actually capture this transaction. And they're actually valid business cases where we authorize something, we never capture it, we reverse it. So if you check into a hotel, which I think lasted like a year ago now, they'll say we need a credit card to authorize for any incidental charges. So if you trash a room or get room service or something like that, take money from the minibar or take nuts from the minibar or whatever, they'll use that authorized transaction to charge you for whatever that was. So you could log into your bank and see like they've authorized for $100 or whatever the room charge was while I'm staying, and at the end they'll either charge you or they'll release that and won't actually charge you. So they actually support this kind of two-step payment flows, like a coordinated, a distributed transaction sort of flow. And my application then serves as that coordinator. So it looks something like this, where I have now multiple try catches, where the first one is I authorize the card. So I say I want to go ahead and put that money to the side. And then if everything succeeds, then I will go ahead and capture that payment later on. Now I put a try catch down there because something can also go wrong with the capture phase. So if something goes wrong in that second part, then we may log something, notify an administrator, and the administrator can go to the Stripe admin UI and manually authorize those charges or roll them back, whatever the business case may be. But they do support it. They have this concept of being able to do a two-step payment flow to be able to try to charge the customer, and then later on actually actually take their money. All right, next up, SendGrid. All right, so we're gonna do the same thing as before, look at all four options and see how that makes sense from a business perspective and how it makes sense from a code perspective. Option one, ignore. And we said earlier that, well, ignore, that may seem strange to do in a business perspective, but there are actually valid use cases where we may not want a third-party system or service, that one going down, to affect the overall business transactions. So we have to ask ourselves, should we still be able to take a customer's money if SendGrid goes down? I'm sorry, when SendGrid goes down. Do I want my business to be tied to whether I can send emails or not? I mean, maybe, maybe not. But in this case, the business would probably say, no, I want to be able to take the customer's money, even if I can't tell them I'm taking their money. So that would look something like this, where I would have a try catch around calling out to SendGrid. And if SendGrid goes down, I'm sorry, when SendGrid goes down, then we'll just log the exception and say, well, we're redirecting them to a success page. And there's probably other downstream communications that happen, like when they actually process the order. So, okay, just put a try catch there, and we didn't send it this time, but they'll get it later communication, so no big deal. Option two, retry. Well, so we did the same thing we did before. We Googled SendGrid idempotent, and we got the worst thing a developer can see when they try to Google a problem, which is a Stack Overflow question with 1,000 upvotes, no answers, but a ton of comments. So basically means no one has a solution for this, but everyone has this problem. So here we're trying to do idempotent sends for emails, but that's just not possible. SendGrid, their whole business model is about getting the emails out as quickly and as fast as possible, quickly and resilient as possible. So when we call to SendGrid, they're going to send that email within milliseconds. And that's their whole business model. You call us, we're going to send an email. So if they had to put something on top of that, like Stripe did, which is you call me and I'm going to look up in some table or database or something, have you called me with this idempotency key before? Well, that's going to add a lot of overhead to the operation. And SendGrid is not about that. They're about getting things out as fast as possible. So they say, no, we don't do that. If you call us twice, you're going to get 2 emails. So we don't call them twice unless we want duplicate emails. So I go to the business and say, do you want the customer to get at most 1 email, 0 or 1? So if the call fails, they just don't get the email. Or would you like them to get at least 1 email? That is, if I call them twice, they get 2 emails. And the business, of course, says, no, we want exactly once emails. They always do, right? They're always just exactly once everything. But that's just not possible with distributed systems. You either get exactly once processing by putting something on top of it, like idempotency, or you get at least once or at most once. That's really basically your 3 options there. Exactly once by having idempotency, or you have at least once or at most once. You can't have it all. So it's really up to the business there about how they want to handle it. They may, get upset, yell, cry, whatever, but that's just our options available. We can't really fix that. So we have to decide decide which option they want. Option 3, undo. Well, as much as I would love to have the ability to undo a send of an email or a text or a chat, it's just not possible. We can't unsend emails. Maybe there is like a logical undo though, which I've had to do this before. Apologize. I'm so sorry. Our system went down. We're so bad at our jobs. Very, very sorry. Please take this $10 coupon as a token of our regret. Here you go. I've had to send an email before. I've had to send an email to clients, to customers, to my boss, where something screwed up, system went wrong, and I've had to make good. So this is actually like a possibility in the business world. Maybe they don't have it as an explicit code level option, of course, like maybe don't code in apologies to your system, but definitely could be like a business level possibility to be able to handle this failure. Option 4, coordinate. What does that even mean, to coordinate sending an email? Like I'm gonna type the email in a draft. I'm gonna put it in my drafts, and then once everything succeeds, then I'll come back to my drafts and then go ahead and send the email out later. Well, SendGrid doesn't have drafts. Maybe I can put the email in like a database table, and then later on I go ahead and take the message out of the database or something. I don't know, but SendGrid definitely doesn't support that. So we'd have to put something on top of sending an email to be able to do something like this. Next up, RabbitMQ. Now, RabbitMQ behaves very similarly to emails. It's a messaging system. However, its importance is a little bit higher than sending an email to a customer. So our choices for the options are going to be kind of similar to what we saw in email, or at least the behaviors of the system, but our choice is going to be much more geared towards like the business process being supported by sending a message via RabbitMQ. Option 1, ignore. Now you could say, well, just on like a basic ignore, we probably don't want that because we need to actually fulfill this customer's order, and that's what RabbitMQ is doing, is the order fulfillment via downstream systems. So we don't just want to like try catch and just like throw up our hands, but maybe we can do something similar to a retry where we do a try catch, and then if something fails, then what we'll do is we'll flag the order saying, hey, something went wrong here. So maybe some offline process is looking for orders that need to have their order created event raised, and then go ahead and sending those messages out the door at some point in the future. So this is a valid possibility. It's kind of like a retry, but we're basically ignoring it in the original transaction. Option 2, retry. Well, I look here. I have the resource A succeeding, the database transaction, Stripe and SendGrid, and then RabbitMQ fails. Now, if I retry a message to RabbitMQ, that could mean that I get 2 messages actually sent at RabbitMQ, because the first call could have succeeded. We just didn't wait long enough for a response or whatever, and then we send another message. So RabbitMQ doesn't have any built-in ability to deduplicate or have idempotent messages. Some brokers do. Azure Service Bus does, for example. If you send it 2 messages with the same ID within like 30 seconds or with a specified idempotency key, then it will deduplicate those messages out the door. And that is configurable as well. It's not infinity, so it won't say, remember that message you sent me 5 years ago? Well, you sent it to me again, so I'm not going to send it out the door. So it has a kind of a window in which you can play with to be able to deduplicate messages. But it's not forever, so you could still have the possibility of messages getting sent out the door twice, and RabbitMQ definitely doesn't. So that means that it's not really RabbitMQ you have to worry about, it's all the downstream consumers who are actually consuming the message that I'm publishing on RabbitMQ. So I would have to go to all these downstream systems and say, hey, cool story. I'm going to send you multiple messages of the same messages, multiple copies of the same messages. Are you okay with that? And of course, they say, no, we're not okay with that. None of our systems are built to be able to handle messages coming in more than once, although they should be. And so we could have the possibility where those messages get consumed multiple times and potentially maybe multiple orders get fulfilled or something. So we'd have to make sure those downstream consumers can actually process the message more than once. Option 3, undo. Oh, again, even more complicated than the email. You can't unsend a message. And a compensating undo message would be weird. So that'd be like, process order, or order succeeded. And then 5 minutes later, haha, just kidding, order wasn't succeeded, event. Go ahead and undo everything. That'd be a little bit weird. So we'd have to have like a compensating message like order canceled or order failed, and make sure those downstream systems can handle the logical undo event of whatever that was. So like in the fulfillment, if they've already shipped the order, then like, well, they just, they shipped the order, they ship free stuff to the customer. If they haven't shipped the order, then maybe they can like take it out of the box. So it really had to go look at downstream systems to understand how could they then handle a compensating message. Option 4, coordinate. Again, the very sad Stack Overflow answer or question, lots of upvotes, lots of comments, no accepted answers because you cannot coordinate a transaction with RabbitMQ. You can try, but RabbitMQ and really any other broker these days does not support a formal distributed transaction protocol. They may support something kind of like it with a confirmation to say, I'm going to send this message and then you have to wait for my confirm. But again, it's not going to support any of that out of the box, like an actual two-phase commit protocol. So, this like Bill at this point, my coworker, was not feeling better about life or things in general because we put all these different third-party services up there and said, okay, let's go ahead and map out the different options for us. And like some of them work for some of them work for others, but nothing that really made us feel great about things. And honestly, our code started to look really, really ugly. So I said, let's take a step back. Maybe the actual problem here is that we're trying to do too much at once. We're trying to fit too much code and too much behavior and logic in that button click for the user. So can I avoid exceptions by breaking the process coupling that we've introduced? So we looked at each one of these and said, do we have to do this operation now, or can we do it in the future? So what about Stripe? Do we have to take their money right this second when they click the button, or can I take their money sometime in the future? And there could be kind of a mix of this where we say, well, what we'll do is we'll try to take the payment, and if the payment fails, then we'll just mark that payment as failed and say, let's go ahead and take this offline. So some kind of offline process, we'll go ahead and try to process the order and then notify downstream systems. So the customer, we'll just say it succeeded, but really behind the scenes, like the payment failed for whatever reason, and we'll go ahead and fulfill this order offline. This is actually what most e-commerce systems do these days. They don't necessarily tie themselves to the success or failure of posting a payment immediately in your button click. What they do is they may try to take your money, but if something fails, then there's an offline order processor, a human being that may call you to get your order information. So let's say I put my credit card details in, but it's the wrong credit card. Whatever, I mixed up two numbers, or just the credit card expired, or whatever it might be. So instead of giving the customer this ugly, you put your credit card in wrong page, then we'll just say, yeah, everything's great. And then we'll have like a nice, happy human call them and say, hey, I think something went wrong with our processing. Would you mind giving me that credit card information again over the phone? Hopefully they pick up the phone and don't think it's spam, whatever. All right, what about SendGrid? When should we actually send the email for SendGrid? What kind of process coupling do we have between these different operations? What should trigger SendGrid and sending the email to the customer? So we go to the business and say, like, what is the thing that should actually trigger SendGrid sending the email? What is the event? What is the operation that should kick off an email to the customer? Is it inserting an order into the database? Is it committing the transaction to the database? Maybe, maybe not. But really, we want to say that when we charge the customer, when we take the money, that's when the order has really succeeded from the business perspective. And so what we'd like to have happen is when the Stripe call succeeds, then send an email. So Stripe actually supports this with webhooks. And webhooks are a way for you to trigger an operation from another operation from some other system. So the idea here is that when the Stripe call succeeds, when they actually take the money from however that happens, then Stripe will go ahead and make a call to your system and service to be able to do something else. Now, Bill and I actually looked at this, but what we couldn't find were a lot of information about resiliency and retries, nor did we want to necessarily have this happen for every single thing that happened in Stripe. And we also couldn't figure out the authentication and security between these things because it's all kind of internal systems. So we said, well, this could work, but we only have 2 weeks, so we won't be able to get something up and running in time. But it is a possibility. Finally, RabbitMQ. Do we have to send the message now, or can we send the message sometime in the future? Now, the interesting thing here is that this is actually a very common problem with systems that use databases and messaging, that databases and brokers can't be coordinated inside a single transaction. Some of them can, MSMQ, but no one should be using that anymore. But like most of them can't these days. You can't coordinate database transactions and messaging systems together, nor do you really want to. But there's a way for us to get around this. So we showed earlier a couple ways of basically flagging an order in the database for something downstream to happen. And you've probably done this as well, that you've got a flag or some kind of information on a table that says something needs to happen in the future. And you probably got some kind of background process going and looking for records that need processing and then doing something later. So you're effectively treating the database as a queue where you have flags for doing future work. Well, there's a general solution to that problem, and it's known as the outbox pattern. The idea here is that when I need to communicate, formatting, when I need to communicate via a message broker, instead of sending that message immediately, I will temporarily store those messages in my database with the same transaction as whatever business transaction or database transaction is happening, and then some offline process that is pulling those logical messages out of the database and then sending them on downstream to the receivers. So that would look something like this. Instead of me calling, RabbitMQ.publish message, instead I'm going to save a message in my database. I'm just using like a messages table that has serialized messages. And then all this does is insert a row into that database. And that row does not get committed until my database transaction succeeds. So that really ensures that I don't accidentally send a message even though my database transaction fails. So that message will not get saved to the database until my database transaction succeeds. And then I have to have something offline that's like pinging messages, looking at the messages in the database, and then for all the unsent messages, going ahead and sending them out the door. Once the messages are sent, then go ahead and remove that message from the database. Now this again isn't bulletproof. We would still have to have some kind of resiliency on the receiving side because I can still have the bus message succeed, but the removal of the message from the database failing, and so I could potentially still have at least one message getting sent out the door. But I removed the problem of accidentally sending messages when my database transaction fails. So we're still not there. The main problem we have here is that there's still way too much going on in a single button click. I've only shown us solving like one problem at a time and showing how the code would look like with that. But if you can imagine trying to solve all these different problems, all these different ways, like that code is going to get super ugly. There's going to be nested try catches and like this succeeded, but that didn't succeed. So go ahead and undo it this way. And that button click is going to get way too ugly and messy. The truth is that most modern e-commerce systems do not try to do everything in the context of a single button click. Most modern e-commerce systems use some kind of background processing to fulfill orders. And I know this actually because back in the mid-2000s, I actually worked for a very large computer manufacturing company on their cart checkout team. And I was very surprised to learn like they don't actually even attempt to take your money whenever you click the button to place an order. They do almost nothing. They don't validate your address. They don't validate your credit card. Like they don't do anything. All they do is make sure that you've filled in the fields because they will try to have the order being processed offline. But if something goes wrong, then they have a human order processor that's going to call you with this very nice and sweet voice telling you everything's okay, but you just fat finger your credit card. So go ahead and just, can you please tell me it again? And the idea here is that the business wants to maximize the number of orders that they successfully process. They want to maximize the money they get from people. And if I put validation errors in front of you, like it's very common, right? You swap two numbers in your credit card. They don't want any like negative things showing to the customer during this cart checkout process. So they will try to make the order process in the website as dumb as possible to have the highest chance of success to be able to ultimately fulfill your order. So we looked at our workflow and said, for each one of these steps, do we have to do this step right now, or can we do this offline? Now, this is highly, highly dependent on the nature of whatever business transaction you're doing. So this is not a general approach. We actually have to talk to the business to say what makes the most sense. So we went to each step and said, do we have to do this now, or can we do this later? But Stripe, taking the money. You may think, well, of course we want to take their money because we don't want people to place orders when they don't have a valid credit card, or they don't have they don't actually have money in their account, right? For the business, so in this case, they said, well, we can always contact the customer. So we want to make sure that they give us all their information so that we can actually contact them later if something goes wrong. So we're not going to try to take their money now. We'll go ahead and process this offline. Similarly, with SendGrid and RabbitMQ, these are at their heart offline asynchronous systems, right? You don't click the button and have your email open like make sure I get my email like right away. So that's naturally an asynchronous process. So we don't have to do that immediately when you click that button. And the same thing with RabbitMQ. It's already an asynchronous process. So what's a little bit more async on top of that? Now we have to kick things off. Starts our asynchronous workflow somehow. One way of doing this would be something like Hangfire. Hangfire is a jobs processing system that integrates very well with ASP.NET, ASP.NET Core, .NET Core, all that good stuff. And we could just have something that's like, running every minute, looking for things to do in our outbox, and then go ahead and send a message to our order processor to actually do the work. So the idea here is that I've got my synchronous system, which the only thing it's doing now is inserting a row into the database, and my order processor that's processing things offline is doing the real heavy lifting of coordinating these backend services and systems. But now we have to pick, how does this order processor coordinate these activities with these backend systems? Well, a simple way of doing this is known as a routing slip, or routing slip if I was in the UK. And the idea here is that the order processor, the initiator, looks at the message and says, okay, this is the work that I need to do, and will write some instructions on the message itself to say, these are the steps, these are the order in which these things need to happen. So as each different consumer receives the message and does its work, it will then forward that message on to the next step in the process. And the idea behind the routing slip is that set of steps is known up front whenever I actually send a message, and so that each individual consumer is completely ignorant or uninvolved in the overall processing and the overall set of steps that need to happen. So I do something like this. I say, go ahead and route this message to these three endpoints: Stripe, SendGrid, RabbitMQ, and the message will just flow from step to step as each consumer receives a message. Well, this works really well for simple cases, but doesn't work for more complex cases where, like, what happens when, not if, SendGrid goes down and that message consumer fails? Should that affect the next step in the process? Or should I still allow RabbitMQ to succeed if SendGrid fails? So if I have any kind of process triggers or coupling between individual steps, so like one thing should trigger another thing, and then I have maybe success or failure to deal with it, then this is not good enough. So the next step up would be to use a Saga. And the idea behind a Saga is I can't make a coordinated transaction between different distributed systems. So what I'll have is each individual step in the process have a logical undo step to be able to undo something if something goes wrong. And the canonical example is, well, it was canonical, I guess, a year ago, but COVID, is I'm booking a vacation. And the idea here is I have 3 different resources that I need to book individually, but none of them coordinate with each other. So what I'll do is I say I need to book a hotel, a car, I guess if we still didn't use Uber or whatever, and book a flight. And so I make those bookings with each individual resource and make that reservation. And if one of those fails, then what I'll do is do the logical undo operation with a previously succeeding operation. So I would, if booking my flight failed, then I would cancel my hotel, cancel my rental car, cancel any reservations, and then everything's back to where it was before. Now maybe I don't get my money back, but that it would be the logical undo of each of those individual operations. Now this assumes, or it actually requires us to have the ability to cancel individual operations. But we've already seen, as we went through our different options for distributed systems failures, that not all of our different resources support a cancel operation. So Saga, which is great for scenarios where you can actually perform an undo, is still not sufficient for us. And basically when you get to here, your next step is to use a process manager. And the idea behind a process manager is you have something that is, well, managing the processing of these different downstream systems using messaging. Now, process manager is really just a kind of a catch-all phrase for something that uses messages to manage processes, but how it manages what communications it sends out is really up to you. But there's basically 2 main patterns for a process manager. There are lots of variations of this, but basically the 2 main ones are orchestration and choreography. And the main difference between these 2 is orchestration is more command-based. That is, the process manager is telling each thing what to do and when to do it. The other one is choreography, where it's more event-based, where I notify systems that something has happened, but they're all performing those steps independent of each other, and they're not really being directed like an orchestrator. And how I choose between the 2 is by looking at process coupling. So in event-based, there is no coordination between individual resources. So I don't get to pick and choose like when someone does something. I'm just saying, hey, everybody, this thing happened. And then they decide when to do it on their own terms. So there's no there's no triggers or no dependencies between things. But we've already seen that there are some triggers between these things. Like Stripe needs to happen at a very specific point in time. Like Stripe has to happen first, and then the other things can happen. I don't want Stripe to just be on its own. I want Stripe to happen first, so we want to orchestrate that call to Stripe. The other 2 are dependent on Stripe, but they're not really dependent on each other. So SendGrid and RabbitMQ, those really don't have anything to do with each other. So those can happen together at the same time or one after the other. There's no process coupling between those 2 things. So it's a mix. I've got orchestration and choreography. So how does this look? Well, it starts off with a call to my website to say, go ahead and process my payment, process the order. The only thing this does is insert a row into a database, commit the transaction, and it's done. Then I have some offline process that is taking the message out of the database and handing it over to my process manager. So in my click order or click the button code, very, very simple. Insert an order to the database, send a command to downstream systems, and then that's just inserting a row into the database, and then finally redirecting them to a thank you page. Our process manager is taking that message out of the database, putting it into a queue for the process manager, and then sending a message to Stripe to say, hey, I need you to process that payment first. So it's going to send a command to Stripe saying, process the payment. So here's my code for my process manager. It receives the command to process the order. It's going to send a message to the Stripe endpoint to say, process the payment. The Stripe endpoint is a message handler that is taking the messages off of a broker, receiving the message, and then calling my Stripe API to process the payment. Here again, we want to make sure that this is exactly what's processing. So we're going to make sure that our call to Stripe is idempotent, and we're passing through a idempotent key to Stripe to make sure that if I get this message twice, it only posts to payment once. Stripe returns a message back saying, yep, our Stripe endpoint, that is, returns a message back to the process manager saying, yes, the payment was successful, or it could also say the payment has failed. We could do something else there. Our process manager receives the process payment result. It says, if this message was successful, they'll go ahead and publish an event saying my order has been accepted. If that payment was not successful, then maybe we mark the order as needing human intervention, needs an administrator or customer service rep to be able to do something else from there. But it's really a process manager that is in charge of that logic, not the Stripe endpoint. Stripe endpoint is dumb, just posts payments and tells me the results. Publishing an event means that I can have multiple downstream systems and services all handling that message independent of each other. And one of those now becomes SendGrid, because SendGrid is now an endpoint that is just a receiver of that event doing email sending, and that's it. So my thank you sender is a handler for that event. It will go ahead and send an email via SendGrid. And now our distributed systems nirvana is achieved. Now, which one did Bill and I do? This would have been our ideal end state because it would be very resilient to failures. We can manage all the success and failure of each individual system. What did we actually do? We actually did an option about 40 minutes ago. Sorry, I guess I'm gonna end this talk early. We did the undo. That is, we will try to send a payment, and if something fails, we will refund the customer. We went to the business and said, do we need to process this payment immediately? Because this is a reservation system, we actually needed to make sure that we didn't keep that reservation open for a long period of time. We wanted to make sure that if you had the payment to do it, you get it reserved, but if you don't, that's bad on you, and we will refund your money, but you don't get the reservation. But it depends. You really have to go to the business to understand what makes the most sense for whatever business transaction we're trying to do. And so that's why most e-commerce systems do what you see here in some form or fashion, where the only thing to do with the button click is to insert a row in the database. Everything else is offline processing via messaging and some kind of order process manager in the backend. So if you want to learn more about this subject, there's a great book out there called Enterprise Integration Patterns. Lousy name for a book, but it's a book all about messaging. So all of the different things we talked about, all the different patterns you saw are in that book, Enterprise Integration Patterns. Another great ones are the microservices book from Sam Newman. They also talk about orchestration and choreography, especially the newest one, Refactoring Monoliths to Microservices. Talks about exactly all of these patterns as well. So thank you all very much. The code behind this that I showed in snippets is actually on my GitHub as well. So you can see a full running example at github.com/jbarger/presentations. You'll see a distributed systems resilience folder in there, and then you can see all of this code and slides in there as well. So thank you all very much. I hope you all have a great rest of the evening, afternoon, morning, day. I think we'll have some time for questions. And if there aren't any, that's great. I will just have some more coffee.